Okay, so we're going to be covering today the concept of uncertainty, which is going to be part of our textbook, chapters 4.6 and 4.7. So uncertainty is really one of those fundamental ideas in probability because it describes the distribution of what you're looking at. And so, we've been talking about how to establish a maximum likelihood estimate of some variable. And that maximum likelihood estimate is our estimate of the mean. But also quite important is that, well, how confident are we about that estimate of the mean? And that's the notion of uncertainty, which means we want to describe not just the mean of the distribution, but also the variance of the distribution. And so if you're not very confident about it, then your variance is large. Your mean is the same, but you have the large variance. And the reason why uncertainty is important is because it'll describe how we should take our beliefs about things. So when we estimate something, we have a belief about what the variable should be, and then we measure something, and then by uncertainty, it's our confidence that we have on what we are predicting. And so if what we're measuring is very different from what we are predicting, then we should believe our measurement. On the other hand, if we are certain about what we're predicting, then we don't pay a whole lot of attention to what we measure. And so uncertainty gives us this weight associated with how we should combine what we predict with what we measure. And in late 1950s, 1959, there was a guy here at Hopkins, his name was Rudolf Kalman, that formalized this idea and came up with an algorithm that describes how to combine your beliefs with what you measure. And that paper was written at a little house bordering the Homewood campus. It was an institute, a research institute. And I've often thought that, the city of Baltimore should put a statue there to recognize Rudolf Kalman, because in many ways the Kalman algorithm, the Kalman filter, is one of the most important discoveries, engineering discoveries of the 20th century. It's the basis of so much of how we compute things. And this guy did it. Okay, so we're going to get there today. We're going to describe the Kalman filter and how to do estimation, which is the basic idea of how to combine what you believe with what you measure. How do you take these two things and put it together? So the way we've been thinking about estimation is the example that we had on Tuesday, which was that there was some variable x that we wanted to estimate, and we did one measurement here, and then we did another measurement here. And we had these two measures, and from these two measures we combined them to estimate x. And maximum likelihood told us how to do it. So we wrote that y, which is this vector made up of our first and second measurement, we believe to be related to the true variable x, and then there's some noise. And this noise has a variance that we're going to describe by matrix R. And the maximum likelihood estimate of what we think we are located at, our x, was something that was pretty similar to the normal equation, except weighted by this noise R. So that was our maximum likelihood estimate. And we also can describe the uncertainty that we have about this estimate, which is the variance of our estimate. And we can see how that works. So that's C transpose R minus 1, C minus 1, C transpose R minus 1 times variance of Y times this quantity transposed, which is R minus T, C transpose R minus 1 C minus transpose. And when we simplified that, we got the quantity C transpose R minus 1 C minus 1. That was our uncertainty about the our estimate of the maximum likelihood. And one of the things that we realized is that the variance of our estimate is always lower than the variance of the individual noises. So if R was RA, the noise in the first instrument and noise in the second instrument, then this variance in some sense was always smaller than these individual variances. So when you have two measurements, you end up with lower uncertainty than if you had one measurement, which should make sense, right? So your variance should go down because you've made two measurements rather than one measurement. So I want to spend a little bit of time today talking about this uncertainty and give us some examples so we can gain an intuition. Once we have these examples, then we're going to talk about what Kalman did with his equations. So let's begin with some examples of what uncertainty might look like. So suppose we have some variable x, x1 and x2. We have these variables, and we have some variance of the vector x described. So x is some vector x1 and x2, and we have some variance of x. So what is this variance? Well, this variance is variance of x1, covariance of x1 and x2, covariance of x2 and x1, and variance of x2. And this is what we call a variance-covariance matrix of some vector x. And I want to sort of give you a sense of what that means. So suppose that this variance, suppose the variance of x, this vector x, was something that looked like this. 1.1 times minus square root of 2, 0.1 times minus square root of 2, and 2. So let me draw for you what does this mean. So first of all, you notice that variance of x1 is less than variance of x2. So if you draw x1 and x2, so suppose that mean the vector x, which is the expected value, the vector x, suppose that's 0, 0. So I'm going to draw some numbers from a distribution that has a mean 0 and it has a variance that looks like this. I want to see what that would look like. So what I should find is that if I plot x1 here and x2 here, first of all, the mean of my cloud should be here at 0 because the mean of the vector is 0. But secondly, we should be able to draw this with the variances that are shown here. So variance along x1 is less than variance along x2. So the amount of data that we have here should be over a smaller range, whereas the amount of data that I have here should be over a larger range. The second thing that you notice is that the covariance is negative, which means that as x1 increases, x2 should decrease. That's what it means for covariance. So my data should look like this. Just to be clear, the axis of this should be something like this. So small x1, large x2, large variance in x2, small variance in x1, and a covariance that's negative. That's what that means. As one increases, the other one decreases. Does that make sense? Okay, so let's try another one. Say that the variance of x is this, 1 and 2, and these guys are 0. So here now, my data should look, like this. There's no relationship between x1 and x2. Variance of x1 is smaller than x2. And similarly, if I have my variance 1, 2, 0.1 times square root of 2, 0.1 times square root of 2. So now this covariance is positive. So now I should see data points that look like that. Okay, so also we can understand something about the meaning of my uncertainty. So here, the variance of x2 is 2, the variance of x1 is 1. What that means is that I'm more uncertain about the value of x2 and I'm more certain about value of x1, because the distribution is such that its variance is smaller for x1 than x2. So let's now look at the problem of regression, and when we fit our data and form means as well as uncertainties. Yeah. Sorry, what's the problem?
I wanted to just turn off the Wi-Fi.
Oh yeah, turn off the Wi-Fi. Great. Excellent. Okay, this will make things much faster. All right, so when we do regression, we say that what we measure is related to some truth, W transpose Xi, plus some noise. And so we think that noise is normally distributed with mean 0 and variance sigma squared. So what does that mean? That means that when we write this, we're saying that the probability of the data given Xi is normally distributed with mean W transpose Xi and variance sigma squared. And so when we're trying to find the maximum likelihood estimate, this is equal to the multiplication of individual probabilities. And when we find the maximum likelihood estimate, well, that's just our normal equation. Where x is all our data. And the variance of our maximum likelihood estimate is which is equal to variance of y is just sigma squared. So then my uncertainty of my maximum likelihood estimate is just sigma squared, and x transpose x cancels x transpose x minus 1. I just get x transpose x minus 1, since this is going to become a symmetric matrix. So this is my uncertainty. This is my mean, and this is my uncertainty that I have for my estimate of the mean value. So I want to show you what that looks like when we actually do regression. This is measurement noise. And this is my data. Right, x's were given to me. That's a matrix that includes all my inputs. Sigma squared is my noise. And so this tells me that my uncertainty about the thing I'm estimating, W, depends on the data that you gave me. Yeah.
Variance of y given variance of y.
Yeah. Very good. So let's try this on a few examples to see what kind of variances we get. So suppose here's my data set. So I have two variables, x1 and x2, and I have some measurement y, and suppose that I had an sort of an uncorrupted measurement. I'm going to call it y star, and then I have the actual measurement y, which is y star plus epsilon, which is the noise that I get. So of course I don't know y star. So suppose on my first trial x1 is 1, x2 is 0, y star, if I had it, was 1/2, but in reality, you know, it's some other number. Let's say 1/2 plus noise. So let's do it again. Again, you give me 1 and 0, and again I have 1/2 plus noise. 1, 0, again 1/2 plus noise. So let's do it 4 times. So you give me 4 data points, and for each one of these times you're going to give me a different y, right? Because each time you get a different noise. And then finally you give me 0 and 1, and you still have 1/2, and you have 1/2 plus noise. So okay, so let's form our problem. So we say y is equal to xw. So this is y. Y is a vector, 1/2 plus noise, 1, 2, 3, 4, 5 times. So we have 5 values here. Sorry, not this one. So this is all right, I don't know. Hopefully what's the problem? All right, so X is a matrix, and here's what it looks like. X1, X2, X1, X2, X1, X2, 2, X5. So what this looks like is 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. And W is what we're trying to find, which is a 2 by 1, W1, W2. So we find the maximum likelihood estimate of W, which is okay. So that's our normal equation, which is X transpose X minus 1 X transpose Y. So here's our X matrix. We're going to transpose this, multiply it by itself, multiply and then invert it, multiply by X transpose Y. And we can find also the variance of my maximum likelihood estimate, which is sigma squared times X transpose X minus 1. So what is this X transpose X is the thing that I want to draw for you. So when I find my W, it's going to be normally distributed with mean. So what is the mean of W? So look at this equation. 1, 0 gives me 1/2. 0, 1 gives me 1/2. So what's W1 and W2? Say again? 1 times something plus 0 times something is 1/2. 0 times something plus 1 times something is 1/2. 1/2, 1/2. Good. That's the mean. And its variance is going to be this quantity. So it's going to be sigma squared times this x transpose x minus 1. This times itself inverted, which is going to become a 2 by 2 matrix, and here's what it's going to look like. 0.25001. So my mean for the weight that I'm estimating is 1/2, 1/2, but its uncertainty is 0.25 and 1. Let's see, what does that mean? So it says that my uncertainty for W1, variance of W1, is low. Why? Because you had 4 times that you saw x1. You saw x1 4 times. But you only saw x2 once. So your uncertainty is 4 times larger. You never saw them together. So your covariance is 0. So the variance of the maximum likelihood estimate is telling you something about the data that you had. Your data was a whole lot of x1s, so we're pretty sure about W1. Not very many x2s, we're uncertain about W2, and no case where the two appear together, so their covariance is 0. All right. So let's do it again. So suppose now we have x1, x2, and y that looks like this. So data is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 1/2. So now my X matrix is 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. And my maximum likelihood estimate of the weight is going to be another normal. And what's going to be the mean of WML? Same, hasn't changed. And its variance is going to be sigma squared, whatever the noise is in my measurement, times a matrix, which in this case is going to be 1, minus 1, minus 1, 1.25. So let's look at this. So this is telling me that I know a little bit more about x1 than about x2, because the variance of x2, sorry, I know a little bit less about W2 because its variance is higher than W1, and the reason for it is because I had 5 instances of x1, only 4 instances of x2, but most importantly, because x1 and x2 appear together, there's covariance between them. Now, what's interesting, yeah, I'll tell you that. Good question. Why is this negative? Why is the covariance negative? So they appear together, right? The reason is this. You have an equation that says y is equal to W1x1 plus W2x2 plus noise. Right? This is what we're trying to fit. In this equation, if you have x go up, x2 must go down. So basically the variance here is telling me something about the weights. If W1 goes up, W2 must go down. And this is what this is reflecting. Let's do another one. So suppose we have a scenario where I have 0, 1, 1/2 plus noise. 0, 1, same thing. 0, 1, same thing. 0, 1, same thing. 1, 1, 1 plus noise. So again, my weights are going to be normally distributed with mean 1/2 and 1/2, and the variance now is going to be 1.25 minus 0.25 minus 0.25 and 0.25. So I'm pretty uncertain about W1. Why? Because X1 was non-zero only once. Pretty certain about X2, about W2, because I got lots of measurements that's associated with W2, and only once where they were together, and so a little bit of covariance between X1 and X2. So my W weights is going to be centered out here at 1/2 and 1/2 with a negative covariance, and it's going to look something like a cloud of uncertainty for my W is going to look like this, with a mean here. Okay, so maximum likelihood gives you an estimate of a mean and an uncertainty about it. And these are the key variables that Kalman used to try to say, well, how in principle we should do estimation. So maximum likelihood has two problems that it can't solve. The first problem is can't include prior knowledge. Let me tell you what that means. So I give you some data and you form a maximum likelihood estimate. What you can't do is to say, I had some prior belief of what the data should look like. And I don't know how am I going to combine my prior belief with this measurement that I got. So I can fit your measurements to my model. But what if I believed that these weights should have a certain value? How do I do that? How do I combine my belief about what it should be to the data you gave me? And that is a problem of how you're going to integrate knowledge, your prior knowledge, with your current measurements. And that's what the problem one of the problems that it can't do. And the second problem is that in principle we want to be able to combine repeatedly prediction with measurement. And so we want to have an algorithm that allows us to update our beliefs every time we make a measurement. And that's what that was a problem that Kalman tried to go after. Now, if you look at his paper, what he's talking about is how do you take a measurement from something, and in this case it's a dynamical system. It's a rocket that you have sent off, and you take telemetry from it, and you want to estimate its position. And so that's a dynamical system. Its position is changing in time. You're taking data. And what you have is that you have a model of its physics. You have a sense of where it should go. And so, if I take a measurement here, next time I take a measurement, it shouldn't be out here. It should be someplace close to it, right? So I have some sense of how things should evolve in time. And I want to be able to take that information that I have and make sense of the data that I collect based on that structure that I have. So in principle, you can use these techniques that I will show you to make estimates of parameters. But I want to start with the way we've been doing learning problems, which is basically estimating W's. So I'm going to present the problem to you, not the way Kalman presented. The problem that he was thinking about isn't the problem that I'm showing you, but this is the problem that we can understand it based on the math that we've been doing using the same principles. Once we understand how to do this, then we can do dynamical systems. So the basic problem is this. You have some estimate of something, W, and you want to update it based on something that you had before, and you're gonna make some measurement, and you have some estimate of how things should have been. This is your prediction, and I'm going to put something in front of this. I'm going to call it K, and this is called the Kalman gain, which is basically how much to learn from error. I'm going to introduce some nomenclature here. So I'm going to put a W of n given n as a function of W of n given n minus 1 plus my Kalman gain times what I measured minus what I predicted. Okay, so let me describe to you why did I write it this way. So this W, what that means is that this is my prior belief. Before I saw this data, I had a belief about my W because I had seen n minus 1 data points in the past. So at trial n, given that I've seen n minus 1 data points in the past, I have a belief about my weight W. I see some input x, I multiply these two, I get a prediction. This is my prediction, y hat in trial n. I have some observation. And here's my prior belief. I combine the two with this gain here, and I form a posterior belief. So W of n given n means that your belief on the nth trial, given that you've seen n data points, depends on your prior belief before you saw that data point, plus the error in your prediction times this gain k. Okay, and the all right, so hopefully, okay, we got it back. Okay, so the problem is, this is the Kalman gain. What is the optimum value? What should it be? And what does it mean to be optimum? So we have to have a cost function. We have to be minimizing something. So the problem is, given that I have a prior belief, I make a prediction based on my prior belief. I make an observation. And now I have to update my belief. How much should I change my belief based on the error that I've seen? Well, the question can be answered by saying, well, what is it that you're trying to do? And what Kalman said is that what you're trying to do is to minimize your uncertainty. So if you could define uncertainty, find a way to minimize it, then the optimum K, the optimum gain associated with how much you should change your belief, is that variable that minimizes uncertainty. So what we're going to do is describe uncertainty, which is the variance. So we're going to form variance of our posterior as a function of this quantity, find the K that minimizes that variance. And that's the Kalman gain. So you can see that it has the flavors of a Bayesian approach, right? It has a prior, it has a posterior. And when Kalman did it, he didn't know about Bayesian stuff. He wrote it as I'm going to show you, which is to describe uncertainty, the variance, minimize the posterior uncertainty, and then you find the Kalman gain. And in the case of a Gaussian noise distribution, what we're going to do is precisely a Bayesian formulation of a posterior. But we're going to get an algebraic solution to it. So that's where we're going to go today. I'm going to show you how to do it. Now, before we get there, the important question to ask is that what do you mean by minimizing variance? Because remember, variance is a matrix. In principle, you have many variables. And so, what do you think he's going to minimize? What's the scalar measure of a variance? Some kind of norm. Yeah. Norms are hard to find derivatives of. So he's going to use the trace. which is the sum of the diagonal elements. And if you think about why that makes sense for a variance matrix, because the diagonal elements of a variance matrix are the variances of what? The individual elements of the vector. So by minimizing the variance of the individual elements of the vector, you're also minimizing the covariances, because the covariance is just a multiplication of the individual variances. Okay? So what we're going to do is as follows. We're going to say this is the equation that describes how we're going to update our belief. We want to find this k, which in principle, depending on what y is, so y can be a vector, of course. In this case, I've written it as a scalar, and we're going to find it for a scalar, but in principle, y can be a vector, and k in that case is going to become a matrix. And so, what we're going to do is to find how much to learn, how much to update our belief given that we have made a measurement. And the answer that we're going to see is based on the intuition that I hope you have, which is that it depends on how much do you believe in your prediction. So if your prediction has a low uncertainty, then you should not learn a lot from your prediction error. But if your prediction is associated with high uncertainty, then you should learn a lot from your prediction error. Does that make sense? So your uncertainty about your belief should dictate how much you should learn. Your belief is your prior. You come to the task with a prior belief. Based on your prior belief, you make a prediction. Then you actually do the measurement. And then you see that there's a difference between the two. And what the result we're going to find is that you will change your belief, form the posterior, by comparing not just your error, but also by looking at how certain you were to start with. If you were really certain, you're not going to change your belief very much. And you're going to update your belief afterwards. So let's go through it and let's see what we get. So that's our basic equation. So if we write it a little bit more expanded, we get something like this. So what is y? What is the measurement that we're making? Well, we believe that that's associated with the truth, w star, some true measure of w, plus there's some noise there, epsilon, and here's our prediction. Okay, so we want to find k, so that it does what? It minimizes the trace of the posterior variance. So what is variance here? So we're going to define variance of w of n given n, my posterior weight. I'm going to define it via some matrix P of n given n. And my variance of my prior weight, w of n given n minus 1, I'm going to write it as P of n given n minus 1. So this is just some matrix notation to describe what do I mean by variances. Okay, so let's write the posterior weight as a function that depends on the prior weight plus this. So all I did is to just write it out as a function of my prior plus the other terms. So now let's find the variance of this equation. So the variance of the left side is P of n given n. That's equal to this term, which is variance of w, which is P of n given n minus 1, times this quantity transpose plus this term has no variance because there's no random variables here. This term has a variance, which is variance of epsilon. And suppose that epsilon is normally distributed with mean 0 and variance sigma squared. So we're assuming that we're making scalar quantity estimates. So y is a scalar. So then variance of this is k of n transpose times sigma squared. Okay, so what we want to do is find k of n that minimizes trace of the posterior uncertainty. So the problem that Kalman was going after was as follows. How do I set my gain of how much I'm going to learn from error so that once I learn from error, my posterior is such that its uncertainty, P of n given n, is as small as possible, where small is defined as the trace of the matrix. So what we're going to do is we're going to describe the trace of this matrix, trace of the posterior, and then once we find that trace, we're going to try to minimize it by finding the k. So we're going to find the derivative of a trace. So, okay, to do that, I'm going to have to do a little bit of work. So I'm going to first multiply out this equation. Of course, once we find the trace is a scalar, so our derivatives, we know how to do those. All right, so I can simplify that. Since this is a symmetric matrix, on variance, covariance is a symmetric matrix, this term here and this term here are the same. I can add them together. So I get P of n given n minus 1 minus 2 times Okay, so there's our posterior uncertainty. As a function of prior uncertainty. This is the prior uncertainty. Before I took my data, here's my uncertainty about W. After I took my data, here's my uncertainty about W. And what I want to know is that how do I set K so I minimize some measure of this posterior uncertainty, in this case the trace. So we're going to find the trace of this posterior uncertainty, this matrix here. Well, trace is a linear operator, so I find the trace of this equation. So I take the trace inside, I find the trace of this matrix, And so what are we going to be doing is that trace is just a sum of the elements of the diagonal. We're going to find that sum, then we're going to take the derivative of that sum with respect to k, the thing that we're after. Why? Because we want to find a k that minimizes the trace. So we're going to define the trace, then take the derivative of the trace with respect to k. Trace is just a number. So when we find this derivative with respect to k, we get, the vector that we're looking for by setting it equal to 0. So let's write the rest of this equation. So I get minus 2 times the trace of this quantity plus trace of this guy here. Well, this is just a scalar, so I can bring it outside. And then I have the trace of this matrix. All right, so what is this matrix here? Kn, Kn transpose. K is something that looks like this. Kn transpose is something that looks like this. And when I multiply this, I get a matrix. And the trace of that is just these elements here. So this trace here is just equal to K of n transpose K of n. That's what that trace is. Ugh. Okay. So this is equal to the trace of the prior uncertainty minus this term here, trace of this element here. K is a vector downward. X times P is a matrix. X is a vector. When I multiply these guys, I get a vector that's running like this. And so the trace of this times this is equivalent to minus 2 times Kn transpose P of n given n minus 1 times x of n. This is just a scalar now. Plus that quantity in the parentheses, this quantity here, times K of n transpose K of n. So the trace is the trace of the prior minus 2 times this scalar quantity plus another scalar quantity times this scalar quantity. So now what I want to know is that, well, how do I minimize this? So I want to find the derivative of the trace of the posterior with respect to K of n. Well, that's equal to minus, the first term doesn't have a derivative with respect to K. The second one, this is just going to be this part of it, K goes away. And then here I'm going to have x of n transpose P of n, n minus 1, x of n plus sigma squared, derivative of this, which is 2 times K of n. I set this equal to 0, and I solve for K of n. So I get K of n is going to be equal to this term This is the Kalman filter. So what we did is we found the optimum gain, and let's see what it means. Let's look at this term here. this term is the variance of our measurement. How uncertain we are about our measurement. Why? Because remember, we had y was equal to x of n transpose w plus sigma. And so this term here is the variance of y. This tells me that you should take what you are trying to do, learn, and your gain should be inversely proportional to the variance of your measurement. It says that take your prior uncertainty and use it as the numerator. The denominator should be your uncertainty about your measurement. So this is saying that you should learn based on the ratio of your prior uncertainty to your measurement uncertainty. The greater your prior uncertainty, the more you should learn from error. The greater your measurement uncertainty, the less you should learn from error. So that's the common gain. Okay. So the next step that we have is that after we learn, we have to form a posterior uncertainty. How uncertain am I after I've learned? And we had an equation a little bit back. So here's our equation that tells us what our posterior uncertainty is. I'm just gonna write it down again, so we have it down here. So what I want to form is that I have a belief, I make a prediction, and now I have found k, which tells me how much I should learn from the prediction error. But next step is that, well, how uncertain am I after I've learned from this? So I have to have not just the mean of the posterior, but also its variance. So that's what P posterior, that's what I'm going to try to write for you here, P of n given n. So from the above equation, we had that was equal to P of n given n minus 1 minus 2 times k of n, x of n transpose, plus k of n times the scalar measure Okay, so this was the equation that we had, that we found its trace, and we minimized it with respect to k. All right, so what is this posterior uncertainty? Well, that's the prior uncertainty minus, so this k here, I'm just going to keep it here as it is, 2 times k of n, xn transpose p of n, n minus 1. But this term here, we can simplify. Why? You notice that there is this term here, this term, times k. Well, k itself has this inverse in it. So if I replace k, its representation, here, then this term is going to go away. And what I'm going to get is this plus k of n, xn transpose, p of n, n minus 1. Because this cancels the first term in k, which is this inverse. So to simplify that, I have p of n, n minus 1, identity minus 2 times k of n, x of n transpose times p of n, n minus 1, plus this minus 2 and plus 1 goes away, so I just get one of those. Ugh. All right, this goes away. Just get a plus here. So my posterior uncertainty is minus. becomes less than my prior uncertainty. This is a second important equation for us. So just to summarize, I had my Kalman gain was equal to my measurement noise this is how much I should learn from my prediction error. And after I learn from my prediction error, my uncertainty about my prediction, my uncertainty about my weights, has been reduced from my prior uncertainty because I just took another measurement. This is my prior uncertainty. My posterior uncertainty is related to my prior uncertainty by this update. So what basically that means is that every time you take a measurement, your uncertainty about the world goes down. So let's summarize. Let's summarize our story. Okay. So you have some inputs that you can measure, and you have some outputs that you can measure, and then there's this W that you want to measure. And you are given data. And so, you begin with some prior belief. W1 given 0. So you haven't been given any data. So you have some prior belief about what the weights should be, and you have some uncertainty about those weights. P of 1 given 0. You haven't been given any data. But to start with, you have some prior beliefs about what they should be. On every trial, you form a posterior by combining what you believed before the prior plus some gain associated with what you measured minus what you predicted. So this is your prediction error. This is your gain that you're going to learn from. What is this gain? This gain is the Kalman gain. And after you learn from that single data point, you update your belief as well as your uncertainty about that belief. And so now you formed a posterior uncertainty, you have a posterior mean. And now what you say is that what is my prior on the next data point? Well, my prior on the next data point is my posterior on the prior data point. So this is our story. We begin with a prior about the mean and the variance of the parameter we're trying to estimate. We make a prediction based on that prior. We compare that prediction with our observation. We update our belief based on a common gain. And here's the common gain. It has to do with our noises in our measurements, our prior uncertainty, and the data that we saw on that measurement. This is the gain that we're going to have. We're going to update our belief based on the measurement error and this common gain. That gives us the posterior weight. When I formed a posterior belief about this parameter, I also form a posterior belief about its uncertainty. This is my uncertainty about my posterior. Then I say, okay, on the next data point, I'm just going to forward in time. My prior on my next data point becomes the posterior on the previous data point, and so forth. And this is how you forward data point after data point. Okay, but we're not done. All right, what if we had a dynamical system? What if our x's led to y's from w's, but that from trial to trial there was some change that took place in the w's? So what this means is that I think that w of n plus 1 given n is related to w by some matrix A. So it is not the case that on the next trial, W is going to be the same if there is this transition that's taking place in time based on some matrix A. So this is going to tell me that my posterior in trial N is going to be related to my prior in trial N plus 1 by this matrix A, because there's this transformation that I believe takes place in my W. So for example, you might believe that your weight should decay towards 0, in which case this A is going to be something less than 1. So if that's the case, then what that means is that your posterior belief is related to your prior belief based on this. So in this model, the relationship between the posterior and the prior is described by this A matrix. Whereas in this model, so this model assumes everything is stationary, nothing changes. So therefore, when I finish with one trial, I just shift forward my belief to the next trial. Here, there's a belief that there is a change from trial to trial, and that is described by this matrix A, which describes how I will forward in time my priors and my posteriors. So this is how we move slowly towards state space models. Models that say things that I'm estimating are not stationary. What I'm estimating is the best that I can do for this data point, but in time when I see it again, there's going to be some transformation from this time to this time. And it won't be the same thing. And that's described, in this case, by this dynamic here, A. And that's the direction that we're going. Okay, so let's summarize. So the Kalman filter, at its core, is about the idea of writing a relationship between measurement, your belief, your prediction, the error that you have between what you measured and what you predicted, and then updating your belief. And in updating your belief, you want to do it in a way that maximizes your certainty, which is to minimize the uncertainty. So you form a posterior after you've learned from that measurement, and you want it so that that posterior has this characteristic where its trace of the uncertainty matrix is as small as possible. The Kalman gain is a way to do that. And it's basically saying if you were uncertain about your belief, then you should learn a lot from your measurement error, your prediction error. If on the other hand, you were certain about your belief, then you should not pay too much attention to what this particular data point was. Okay, any questions? Yeah. Yeah. So we skipped a lecture. So basically, my lecture came one lecture too soon. Next week, you're going to have Fourier series. But for today, your homework is the lecture associated with the Kalman filter. You'll see it, which is the next line on your webpage. Estimation theory. Yeah.
Why is it called a filter?
Right. So it's a filter in the sense that it is filtering data, which is your measurement, but weighing it by two things. What did you predict that data point should be? And what was the uncertainty that you had about that data point? It's a time domain filter. Yeah. Right. There you go. Yeah. Yeah.
Our, like, the last part about the A's, how do we transition W to
Yeah.
N plus 1? If we, like, make it up and it doesn't make any sense,
Yeah.
will a Kalman filter adjust for that?
No. So the key idea of a Kalman filter, and in fact estimation theory, which is what we're talking about, is that your model doesn't change. Your model parameters don't change. What we're estimating is something about this parameter here, this variable that we don't know. But the structure of the model, which is the structure here, X is conditioning Y, W is conditioning Y. There is some transition matrix A. There are these noises that we have, sigma squared, somebody has to give that to you. Because you can't estimate the Kalman gain unless you know the noises. So in estimation theory, we have a model that describes how our data was generated, and then we're going to go and use that model to estimate something about it, in this case the parameter, the variable w. When we do system identification, we neither know w, we also don't know a. So we'll get there. So we'll get to algorithms that help us do system identification. That's when we learn about expectation maximization. That's an algorithm that'll help us not just estimate the parameter that we're looking for, w, but also what's a. There are other variables. So let me give you a sense of things. So what are the kind of problems that we eventually want to get to? So we have some dynamical system. And then we have some measurement from this dynamical system. So the problem might be we don't know x, so we just have y that we've measured. Let's see if I can make this. Ugh. All right, ignore this y here. So what estimation theory says is that given y of n, tell me x of n. That's what we're working on now. We're saying you did some measurements, y of n. What is x of n? That's estimation theory. That's the Kalman gain. That's what can tell you how to do that, how to solve that problem. What I haven't told you is that given y of n, what is this? That's system identification. I neither know the state of the system, I don't even know the structure of the system. So before we can get there, we have to understand state estimation. If you had the structure of the system, how would you in principle find its state? Kalman filter, state estimation. Once we have that, then we'll get to the harder problem, system identification. How do I even know what these parameters are, what the structure of that system is? We'll use EM to solve that problem. So just to give you a sense of things, so in here, the way I wrote this problem here, you do something to the system. You give it an input u. It has an internal state x that changes, and it gives you an output y. And what you want to know, and it's a dynamical system, right? So you give it a u, and it does something. You send a rocket in space, and it moves. And you make measurements once in a while. And you want to know, what is this dynamics? How is this input u changing this system? And what is the state? Where is it located at any time when I make some measurement? It's going to rely on the Kalman filter. But Kalman filter is only going to be one of the steps. Okay, so the problem that's expectation maximization. The problem that we're going to use in a few weeks. Okay, any questions? All right, have a good weekend. I'll see you soon.